Projectiles launched at an angle. So when physics students play football, this is the type of thing that happens. Pause the video, see if you get this comic strip. What I'm going to do is I'm going to show you an animation of a ball that's going to be launched at an angle from the ground. What I want you to watch for in this animation is when the initial velocity in the y direction equals 0, and at what time the initial velocity in the y direction or the velocity in the y direction is going to be equal to 0. Also, I'd like to remind you that if I've got a vector that has some sort of direction that's not one of the cardinal directions, not north, east, south, or west, this vector can be resolved into its component vectors, where you can have an x component and a y component. And don't forget that the vertical component, in this case dy, is going to be the velocity times the sine of the angle, and the x component is the velocity times the cosine of the angle. That comes from the resolving vectors part that we have already done in motion in 2 dimensions. So here's the animation that we just talked about. This is my velocity vector right here. It's at an angle. The angle would be right here. Here's the x component, which I would find with cosine, and here's the y component that I'd find with sine. So as I step through the trajectory of this projectile, notice that the y component is shrinking and the x component stays the same. At the very top, the velocity in the y direction is momentarily 0. And notice that this happens halfway through the trajectory of the projectile. And then the y component comes back and starts increasing in the negative direction because the projectile is coming back down. And again, the x component doesn't change. So putting it all together again, we can see that at half the time of the trajectory, there is no y component to the velocity, and then double the time is when you've got the final velocity in the y direction, which is going to be the maximum value you can have. So we're going to use the fact that the initial velocity, or the velocity in the y direction, equals 0 at the apex, or the top of the trajectory, and the apex of the trajectory happens halfway through the flight. If we use these two facts, making projectile problems when projectiles are shot at an angle much easier. Here's an example problem. A bullet fired at an angle of 60 degrees with an initial, a bullet is fired at an angle of 60 degrees with an initial velocity of 200.0 meters per second. How long is the bullet in the air, and what is the maximum height reached by the bullet? So let's fill in what we know here. Here's my initial velocity. It's 200 meters per second at an angle of 60.0 degrees. Remember that that velocity has an x component and it has a y component. And we know the y component equals 0 at the very top of the trajectory. So if I can figure out how long it takes to get halfway through the flight path, I can double that time and figure out the total time it takes for the projectile to travel. So I'm going to use equation number 3. All the uniform equations of motion stay the same. The only difference is we're going to add the component of sine and cosine in there. So equation number 3 for velocity in the y direction equals the initial velocity in the y direction plus g times t. I'm going to rearrange this to isolate time. And then I'm going to remind myself that the final velocity in the y direction halfway through the path is 0, because I'm finding the time right there. The initial velocity in the y direction is going to be 200.0 times the sine of 60.0 degrees. And again, that's because Vy is going to be Vi times the sine of your angle. And then this is all going to be divided by negative 9.8. That's going to be the time. So when I do this, I find that I will get 200 times the sine of 60 in the negative, divided by 9.8. I get half the time equals 17.7 seconds. I got to double that because I just found the time to right here. So doubling this, I will end up with 35.3 seconds. So that's the first part of this problem, to find how long it took for the projectile to travel the whole path. I figured out how long it took for it to go halfway, and then I doubled it. For the next part here, there are multiple options as to what equation I can use. As to avoid error carried forward errors, I am going to choose to use equation number 5 because it does not involve time. But you can use equation number 4. You can use equation number 3 with combination of equation number 2. There's a bunch of different ways of doing this, but again, I'm going to do equation number 5. So I want to figure out the maximum height, or the apex here. So I want to find out y. How I would write equation number 5 out here is I'd say dfy squared equals diy squared plus 2ay. And notice I'm using y because I'm talking about the vertical component. So now what I'm going to do is I'm going to remember that the final velocity at the apex is again 0. So rearranging this, it turns into dfy squared minus vi sine theta quantity squared. That's the y component of my velocity, all divided by 2 times a, which is actually gravity. Change that to gravity, equals y. Filling in what I know, 0 squared minus 200.0 times the sine of 60.0 quantity squared, all over 2 times negative 9.8. And when I solve this out, I will find that my height should be 1,530 meters with 1, 2, 3 significant figures. 1, 2, 3 significant figures. So again, this is the quickest way to do this, but you could also use equation 4, or you can use equation 2 with a combination equation 3. This is the easiest way for me to solve for the apex of a trajectory. At this point, you should be ready to try the worksheet that's attached to the Schoology assignment. Read the directions on the Schoology assignment very carefully so you don't do more work than you have to. I will come around and answer questions as you go. Good luck.